Hello, this is Andy from Engineers Academy, and in today's video I'm going to be providing an introduction or an overview of cams. Now we're going to start by looking at the various different applications of cams, and then we're going to look at the type of cam that can be used as well as the type of cam follower. And we'll look at the associated benefits with the different types of cam and cam follower during this video. So to begin with then, what is the purpose or the application of a cam? Well, a cam is specifically designed to convert angular motion into linear motion. And as you're going to see throughout this video, we can achieve various specific paths of movement using different types of cam. And in actual fact, we can design cams to achieve almost any motion that we might desire. So in this animation, we can see a very basic example of how a cam works. In this example, we have a pear-shaped cam. And what we can see is that during various parts of the cycle, the follower doesn't move, and then at other times in the cycle, the follower is lifted by the cam. And as mentioned, this is just a very basic simulation in order to demonstrate the operation of a cam. If we consider a specific application for a cam that you may or may not already be aware of, we see cams used within a car's engine. Now, in a car's engine, we have cylinders where a mixture of air and fuel is compressed, and that air-fuel mixture is then ignited, causing it to rapidly expand and drive our crankshaft. Now, connected to the crankshaft by a timing belt is the camshaft, and the camshaft has a sequence of cams mounted on that shaft. If we look at the diagram on the left-hand side, we can see this in a little more detail. So as the camshaft rotates, the cams are going to rotate, and they're going to cause the valves on the top of the cylinder to open and close. Now these valves need to open and close, first of all to let the air-fuel mixture into the cylinder, but secondly to expel the exhaust gases after combustion. So the timing of the opening and closing of these valves is very important, and it needs to be directly linked to the rotation of our crankshaft. So that's just one example of an application using cams, where we have rotational movement of the cam being translated into linear motion of the valve. Now, as mentioned previously, there's various different types of cam to achieve different types of motion, and some of the more common ones we have here are a pear-shaped cam, an eccentric cam, which is essentially round but with an offset centre, and a snail cam, where we can achieve a gradual lift and then a sudden drop for a valve. And there's lots of other different types of cam to achieve different motions. If we focus specifically on our pear cam, then we have a number of different stages in our cycle. We have the rise interval, which is the time when the follower is being lifted. We have the dwell interval, so this is when the follower is being held in its upright position. We then have the return interval for closing the valve or lowering the follower. And then we have another dwell interval when the follower is in its bottom position. What we see here is the displacement for one full 360-degree cycle. So next, let's consider the different types of cam. And once again, there's various other different types of cam, but we're going to look at two in particular. We're going to look at the radial plate cam and the cylindrical cam. Now, the types of cam that we've been discussing up to this point are known as radial plate cams. And basically, they're a disc of material of a given thickness. Another variant on the cam, which again translates angular motion into linear motion, is the cylindrical cam. Another name for a cylindrical cam is a barrel cam, as we see here. In this example, the shaft's rotating, we have a cylindrical piece of material, and a groove is cut in that material. Once again, we have a follower, but this time the follower is configured slightly differently, enabling motion of our follower parallel to our rotating shaft, as opposed to perpendicular in the case of our plate cam. So as we've seen there, we have different types of cam, but we also have different types of cam follower. Now, the cam follower sits in contact with the cam, and we're going to look at these for the plate cams that we discussed previously. We have a knife follower, we have a flat follower, and we have our roller follower on the right-hand side there. Now, each of these presents various different advantages and disadvantages, so we're just going to look at each of these briefly in sequence. First of all, on the left-hand side, we have our knife follower. Now, as you can imagine, because we have a single point of contact, these give us very high degrees of accuracy. And in addition to that, because we have a single point of contact, we get low friction or reduced friction, and that's going to improve efficiency. However, the disadvantage with this type of follower is that it's not very good at carrying loads. If we apply heavy loads here, then we're going to cause excessive wear to the tip of the follower. So an alternative type of follower that we can use is the flat follower. Now, flat followers are much better at carrying heavy loads, as you would imagine, because that load is more evenly distributed across a surface rather than resting on a single point. The disadvantage here is they're less accurate. The point of contact is much wider, and as a consequence of that, we actually generate more friction. More friction means a less efficient system. Now, combining the benefits of the two types of follower there, we have the roller follower on the right-hand side. Now, roller followers, because they have a single point of contact, produce very high degrees of accuracy. Again, we have the benefits of reduced friction due to that single point of contact, and due to their construction, they can also carry heavy loads. Rather than sliding resistance here, we'll have rolling resistance, so we're less likely to experience wear on the roller than compared to the knife edge. The disadvantage with this type of follower is obviously cost. They're more complex in construction, they have more moving parts, and therefore they're more costly and possibly require more maintenance or inspection. So just to summarise then, in this video we've introduced cams and cam followers. We've looked at different applications for cams, but particularly for translating angular motion into linear motion across lots of different types of path. We've looked at radial plate and cylindrical cams, and we've looked at a number of different followers, including the knife, flat and roller followers. And at the end we discussed some of the associated advantages and disadvantages associated with the use of each of those followers. In the next video we're going to begin looking at how we design a cam in order to achieve a specific path of motion.